Welcome to Brain Vision.
16.34. So we have a wave with the given properties here that's propagating along a chord that has these properties here. It's density and tension. So first of all, we want to find basically what the p average is, which in this case it expresses it as the average rate at which energy is transported by the wave to the opposite end of the chord. And then we would want to imagine if we have a string that's adjacent to it and they're both like sort of fixed to the same thing, but there's two of them, you know, what's the power that's being transmitted over to here by the identical wave on the other string plus our original one. And then if they're both on the same string, we want to figure out what the power is for various phase differences. So the first thing that we're going to want to just go ahead and figure out right off the start is the wave speed. This is 775 meters per second. Because that saves us the bother of having to, you know, do some sort of, you know, algebraic substitution stuff in our expression for the average power, which is 1/2 times the density times the wave speed times the angular frequency squared times the amplitude squared. So this is 10 watts in our first case. In the second case, we don't have any sort of superposition going on. We've just added another string with one of these waves on it. So that's just going to double the power. Now, for zero phase difference between the two waves on the same string, we're going to basically just double the amplitude, which means that doubling this increases this whole thing by a factor of 4, because 2 squared is 4. So this will be 40 watts. And then for the remaining two, we need to be a little bit more clever. And use the, well, not really that much more clever, I guess, but we need to use the actual equation for what the amplitude is as a function of the phase difference. So this has the phase difference divided by 2 as its argument. So we're just going to go ahead and divide it by 2 right there. And so the amplitude of the superposed wave in this case is 1.618 times the original amplitude. So if we square that, that's a factor of 2.618. So we multiply our original power by 2.618, and we get 26 watts. So now if they're pi out of phase, that means that they're going to undergo completely destructive interference. Because pi is 180 degrees, or half a wavelength. And so because they cancel out completely, the total power is 0 watts.